Excuse me.
Thank you very much, Mel, for inviting me to speak here. Last time I came here when I was a postdoc, so it's been a long time. I'm very happy to be back. Today I'll be speaking about Lehmer-type partition statistics. So Lehmer studied this in 1972, many years ago. But Jeff Legarius in particular has sort of brought attention back to this problem. So I'll go into the details about that later, but let's talk about what Lemmer did. So start with a partition of any positive integer n. So if p is a partition of n, that means you can write n as sum of these numbers a1 plus a2 plus a3 and so on. And just to make sure that the order doesn't matter, we write this in the decreasing order or non-increasing order. So all these aj's are positive integers. Now we define something what Lehmer called the weight of a partition. So note that when we add all these aj's, we get n. But these are all positive integers. What do you get if you multiply them out? So if you multiply them out, it's going to be an integer. So you look at one of this, 1 over the product of the parts, aj. That's what he called the weight of a partition. So once again, you fix an n, you fix a partition of that n, you look at, therefore the parts are fixed, and now you multiply those parts and take the reciprocal of that. And now you could do the same thing, because for partitions, rather than taking all or allowing all the positive integers to be your parts, you could say, oh, I only care about partitions into odd parts, for instance. I'm only allowing myself to write n as sum of odd numbers. So you could take any s in particular, and let's take this notation WNS, which is what Lehmer used. So I'm sticking to the original notations. And now you add all these weights. So it's for a fixed n, you have these many fixed number of partitions of n, and for each partition you have the weight WP, and you add this up. So you are adding all these rational numbers. So you will get a rational number. Question is, what happens when n goes to infinity? What can you say about this? Is there some regularity? Can we say something about this? You could also ask the same question, where you, rather than adding all partitions, you are adding only the you are summing only over the partitions where the parts are distinct. So there is no repetition among the parts. So let's look at an example. So suppose I take n equal to 6. I have 11 partitions of 6. So first partition is 6 itself. So the weight of this partition is just 1 over 6. The next partition is 1 plus 5. So the weight of this will be 1 over 1 times 1 over 5. So I get 1 over. For 2 plus 4, it's 1 over 2 times 1 over 4. You get 1 over 8. And you get that. So now if you add all these rational numbers, what would you get? And for this example, W of 6 is this rational number, which is about 3.2. And if I only allow the distinct parts, which means I'm only looking at these colored ones. I'm not sure if the color is visible, but the point is that now you have very few partitions, because you are not allowing repeated parts. And in this case, your weight W star 6 is about 0.6. So as n grows to infinity, you would expect that if you allow only distinct parts, you are only going to get something much smaller in comparison to all partitions being allowed. But is there a formula? Can we say something about this? So what Lehmer did was, he looked at the generating function of this statistic, so WNS in particular. And before looking at the generating function of this directly, he multiplied this by n factorial. Note that in the beginning, these were rational numbers to start with. If you multiply by n factorial, you end up getting integers, because in the sum I have WP, if I multiply each of these weights by n factorial, I end up getting something like n factorial over a1 factorial times a2 factorial and so on. That's like the multi-binomial here, multi-binomial expression, and times some a1 minus 1 factorial, a2 minus 1 factorial, that's already an integer. So this ratio over here is an integer by multi-binomial expression, and this is also an integer, so you end up getting an integer. And he looked at for both these unrestricted and distinct parts. He looked at this generating function, but in terms of this n factorial included. So I mean, you are looking at WNS, generating function of WNS, which is a n divided by n factorial. But he writes this n factorial with the x part. Similarly, you can do this for the f star or for the distinct parts. And just to show you the table, you could say, is that already an evidence? We are only looking at 10 numbers in the table, but it turns out that this already sort of tells you that there is some limit phenomena going on. It's pretty regular. In the graph, it's drawn up to n equal to 40, and you can already sort of start making conjectures that, okay, this limit might exist, and this dotted line is about 0.5615. I will tell you what exactly the constant is in a bit. But the point is that both these sequences, for the distinct parts as well as the unrestricted parts, they seem to converge to the same constant. And the question is, what's that constant? And it's given by e to the power minus Euler constant. So he showed that as n goes to infinity, for the distinct parts, it grows like e to the power minus gamma, and that's the Euler constant. And in order to do this, what he did was started with the generating function, which was f star x, and separated the pole at x equal to 1. So you get 1 minus x sort of separated out. And then once you write it, you can write this Wn star, that's the quantity we are interested in, as a partial sum of this sequence. What are Bj? Bj's are some, okay, so Bj's are just the coefficients of the power series for g star x, which is just 1 minus x. And then when you take the logarithm and let x go to 1, you can separate the part which gives you the singularity, and you get this 1 over n minus this log, and that allows you to get this limit. And we know the asymptotics for some more 1 over n, and that gives me just the gamma, the secondary term for the partial summation. And once you have that, that was the main point. And once you have that, you can apply Abel's theorems to show that, okay, Wn star, which was just this, will also converge to this. Will converge to e to the power minus gamma. So nothing very deep, but just a nice starting point. So once you look at this point, then this is the next, step 2 is the next natural thing. So if you get some nice terms over here, you could expect some nice constants in particular. But the point is that here you see this Euler constant. Okay. Okay. You can ask the same thing when you only allow parts to be at least 2, so you do not allow 1. Why so special? What's so special about 1? Well, whenever 1 is a part, we are multiplying all the parts. So when you are multiplying anything with 1, you are not changing anything. So you would expect that, okay, this should also be the same. So in particular, there is a bijection when 1 is a part and when 1 is not a part. So in this example, we have partitions. So this is 4 plus 2 plus 2, that's 8. It's a partition of 8, but you can relate it to a partition of 7 by removing 1, and you will get the same weight because you were just multiplying once. So that was not anything. Okay. And also when you sum them, Wn minus 1, you end up getting the Wn of S1, where the parts were only allowed to be at least 2. So then the difference is telescopic, and you end up getting this limit. Again, the appearance of Euler function is visible. Okay, so he also does this for more general sets, in particular where your parts are allowed to be in any arithmetic progression. But in order to do this, he needs these two lemmas. So rather than just removing the or factoring out the singular part, in the earlier case that was just 1 minus x, in this case you need 1 minus x to the power something that's positive, and then you can apply this theorem, or you can for the general arithmetic progression a n plus b, you would need something like this, slightly more general lemma than the top one. And once you have that, you can get results in this direction. In particular, if you only care about odd parts, you get this much larger limit. But if you take and if you allow only parts to be even, that means your n itself has to be even. You are adding only even parts. So in that case, if you have odd n, this will be 0 identically, of course, but otherwise also this is very low. The number is very low. So you could get, and that is the reason why we have this difference of full power of n. This was this times square root of n, and that was 1 over square root of n. And that was because in this case you had a 1 minus x in the denominator. So this is the general thing that he showed for any general arithmetic progression. This is written rather than the usual a mod b, just because I stick the notations that he's using, and this not to write it as b comma a. So okay. Just to show one more table, when you take just this, so this is around 100, but I'm only showing you 5 numbers, and you can already see that the limit is pretty sort of visible. It's like, yeah, you should have some limiting distribution over here, and that's what. So Lehmer, this is from his paper. He wrote this table, and just by looking at few numbers, he could guess that this is what it should be. Okay. So now I want to move on to something that's been more recent. So notations are slightly changed. So you fix your lambda as a partition, and you multiply all those parts. So it's product of the parts. And in Lehmer's notation, 1 over n of lambda was the weight. So it was just the reciprocal of the product of the parts. And now we are just looking at the parts. Sorry, this should have been an n hat. So give me a second. Okay. So these are the more recent terms, even though McMahon and Lehmer had already studied these quantities. And for instance, Lehmer called it the weight of the reciprocal of a partition. In 2022.
Sorry, Amita, could you just check the chat for a moment in case someone's trying to ask you a question? Or not?
There were a bunch in the previous talk there, so I'm not.
I can check. Okay, sorry.
Okay.
And we the one bit bigger. Yeah.
Oh, it has to be made bigger from here.
Control.
Yeah.
So in the upper right, there's a view button. And we can go full screen. That'll help a little at the bottom of that.
Is it better?
Yeah.
Okay, great. Okay, so the same object studied more recently now, but with a different name called norm. So N for norm, just because now we are looking at the multiplicative properties. And the new thing that has been recently, this term has been coined supernorm, which means that rather than multiplying all the parts of your partition, you multiply the primes indexed by your parts of the partition. So rather than taking the product of lambda j's, for instance, in this partition, rather than multiplying these parts, we are multiplying the third prime, the second prime again, and the first prime. So now this is a totally different integer, much larger than the earlier one. So when you take the reciprocal of this, this is going to be much smaller. So the question is, can you answer the question about sum of 1 over the supernorms of lambda rather than just 1 over the norms of lambda, which Lehmer studied? So just a quick reminder, this is what Lehmer studied, and he got this Euler gamma function appearing in this. And we saw that the reason why gamma appeared was because of this harmonic sum. And the question is, would you still get Euler constant over here? And so in the beginning, I mentioned Jeff Legarius. He has been very interested in this Euler constant. For instance, in 2013, he wrote a very nice survey in the bulletin of AMS about the appearance of Euler gamma constant and maybe different connections, the reason why this gamma appears in these different sort of looking problems. And so he gave a talk last year at University of Florida, part of this Ramanujan Colloquium, and he gave a talk and mentioned about these partitions, which he had recently worked out with Sun, who was, I think, at Columbia, or he is at Columbia now. But just before that, Dorsey, Just, and Schneider, they had looked at this. They are the ones who coined this supernorm term, and they looked at it from a slightly different point of view. And then Jeff brought this analytic feature to these questions. And so now the question is, will you still get Euler constant? And it turns out that yes, it will reappear, but for a different reason, not for the harmonic sum, but for Merton's product, because in the when you do summation of 1 over p, you still get the same constant. Okay, so this is what they did. They looked at 2-3 different kind of statistics, basically attached to any partition of n. So in particular, if you just take size of n, that means you are just looking at the number of partitions of n, and Hardy and Ramanujan already gave the asymptotics for that. And for the perimeter of n, so in particular, you can define for a partition lambda of n, the perimeter, which is the largest part, lambda 1, plus the number of parts, which is the length L of lambda, and you subtract 1 from it. Why from our point of view, the subtraction won't really matter in some sense, but the reason, if you see on this, on the right side over here, this is a partition 3 plus 2 plus 2 plus 1. That's the number of boxes in each line. And algebraic combinatorics people have different, like some people look at it from the hook point of view and they would say, oh, this is the largest hook length. And some would say, oh, it's just the, basically you are just consider the rectangle over here, you are just adding the 2 sides. So, but to make a connection over here, you are just subtracting a 1. But these are different ways of looking at it. They also look at max of n, which is basically putting the condition on the largest part of n. So in particular, you can see that the size of lambda is always going to be larger than the perimeter of lambda. So I'm not going to give too many details about what exactly they did, but with some graphs, there was some. So once again, we are interested in this sum over 1 over the supernorms now. If you take one extra sum, which is what this C hat is doing, so W hat is already a sum. If you allow yourself to take one more sum, then you can get some nice results. And that's what they get. They do prove theorems asymptotically. This is given by this. So you do see the appearance of Euler-Gamma function. And from the graph, once again, you can see that this is the case. Okay, so and why the Euler-Gamma constant appears, you can see that they have to, because this supernorm, you have to actually study the prime numbers, and you end up using this Merton's estimates, and the bounds on the nth prime, you can get this full asymptotic theorem. So this is the theorem where they also get the error term and also the secondary main term and so on. So they get this. Other than these 4 statistics, so these are just the lemmas that I mentioned they use, and you will see a lot of primes appearing. Primarily, the reason is because now you are looking at supernorms. Other than that, they make a conjecture that, okay, they could get all these nice formulas because they were doing true sums. But can you say something about the parameter directly, W per? And they say that the data suggests that the limit of W per n is, or n is 1. So in other words, this quantity is asymptotic to n. And we show that with Ritramdhar. He's a PhD student at Florida. That's where Jeff had gone to give the talk in the colloquium. So that's how we came to know about this. And we show that this conjecture is indeed true. So it is asymptotic to n, and motivated by the length that was studied by Lagarius and Son and the norms, we are studying the mixed moments of these two quantities, their joint distribution, and we do have statistics from there also. I would like to end with saying that our methods are very much in the spirit of what Lehmer used. So we do only get the asymptotics, not without the error term. But if we use a different method, we might be able to get the actual error term. But we haven't tried doing that yet. And with that, I will stop. Thank you.
Thank you very much. Are there any questions for Amita? From the room or from the Zoom?
Interesting thoughts. Have you or anyone looked at Lehmer statistics when you have like powers, squares, or?
So for different sets, yes, we have some connected, but we haven't actually tried to. We haven't got the results yet. We wanted to get into this direction about the moments. But yes, we can add, as Lehmer did this arithmetic progression, we could talk about other sets, and that's. In fact, we are trying to get some uniform result where we can sort of talk about the general set and maybe the density of that set. Not.
Sounds good.
And in the beginning, when you defined Lehmer's weight as 1 over the product of the parts,
yeah.
Why that weight?
He just says that this is the weight we are using, just weighted partition. But in recent work that I mentioned from 2022 of Rafael, they are Kenono students. So they looked at, so Rob Schneider has been really into this bijection from the additive number theory to the multiplicative number theory. So you can sort of define a new version of Riemann zeta function, and each partition sort of will give you something related to that. So that is a nice connection in that sense.
Thank you again. Next talk will be by Sandra in a couple of minutes. Give me here first. You did on water?
3 months.